Learning physics-based full-body human reaching and grasping from brief walking references. Generating realistic, physics-based full-body motions for human reaching and grasping diverse objects in various scenes, has broad applications in animation and AR/VR, and holds significant potential for advancing humanoid robotics. Previous data-driven approaches have shown promise in generating human reaching and grasping, but often constrained by the limitations of Mocap data sets. Human interactive skills, however, are highly diverse, and collecting Mocap data is time and labor-intensive, resulting in limited samples and biased distributions. To address this, we propose a novel approach that generates diverse full-body reaching and grasping motions using minimal data, such as brief and easily accessible walking references, thereby eliminating the reliance on extensive motion data collection. We observe, walking motions encompass natural movement patterns and balancing abilities that can be transferred across different actions, providing a valuable motion pattern reference. On the other hand, recent advanced kinematic methods can generate diverse grasping poses conditioned on specific scenes. These poses can be interpolated to form continuous motions. Though lacking physical guarantees and the natural patterns, they can also serve as useful task-specific guidance. Based on the observations above, we propose to tackle the challenging motion synthesis problem by combining two data sources: limited, real walking data and flexible, task-adaptive, but unverified generated data. The key is to determine what data should we generate, and how to effectively combine data while avoiding artifacts and maintaining natural patterns. We first conduct a pilot study to investigate whether real walking motions contain transferable features that can enhance reaching and grasping. Initially, we train a motion critic using walking Mocap and employed to assess a real reaching data set and an interpolated data set. We adjust the structure of the critic neural network to extract segment-specific information first to incorporate local features. We observe that real data exhibits clear clustering features at shallow while deeper features diminish the clustering. The clustering motivates us to encourage new motions to align with the shallow layer features of walking. Overall, to synthesize reaching and grasping motions, we first construct a latent motion skill space. We then train a policy to execute reaching and grasping tasks by leveraging skills from this latent space in a similar flavor to ASE. To enhance the latent space with the necessary skills for reaching and grasping, we generate kinematic motions through interpolation between standing and grasping poses to expand the latent motion space, while the shallow layer skill features are still enforced to align with walking skills, ensuring the preservation of natural movement patterns. We propose a pipeline that generates diverse reaching and grasping through the multi-iteration training. First, we train a low-level policy on walking Mocap, with the discovery and imitation objectives specified respectively by the encoder and discriminator, to map latents to motions in the data set. Next, use a task-specific reward, we train a high-level policy to select the variable for tasks. To enhance the latent space with reaching and grasping, we actively generate kinematic motions to target the hard tasks. The active strategy is to add more data for worse performance task, maximizing the utility of the generated data. Then, the generated data set can be used to extend the space, while the shallow layer skill features are still enforced to align with walking skills, ensuring the preservation of natural movement patterns. We can generate diverse and natural reaching and grasping motions across varying scenes, adapting to different table heights, widths, and initial positions, while achieving a high success rate. Our policy is robust and demonstrates strong generalization capabilities, effectively adapting to various unseen objects and even entirely new categories. Compared to baselines that either lack overall guidance or have divergent objectives for walking and reaching, our method demonstrates a significantly higher success rate and much more natural movements. Compared to other baselines utilizing more flexible part-wise discriminators, our policy shows a stronger ability to maintain balance and recover walking, resulting in better task completion and improved overall motion quality. Visualizing the impact of adding generated data shows that with a small amount, the agent struggles to raise its hands and bend down. As the data ratio increases, it gradually learns to reach and grasp. However, too much data causes it to forget walking skills and focus on generated motions to maintain balance. We conducted an ablation study on the active strategy, revealing its effectiveness with small data additions by targeting tasks that walk data cannot handle, avoiding irrelevant data. We also conducted an ablation study on the feature alignment mechanism. Adding a shallow layer proved particularly effective in refining part-wise patterns, such as preventing excessive torso bending, which contributes to generating more natural motions. Also, feature alignment enhances overall stability, as shown on the left. The left hand raises swiftly, and the left foot steps back quickly to maintain balance when grasping low objects. This coordinated movement is crucial for dynamic recovery. To compare generated data with real-world mocap data, we trained an Oracle policy using high-quality mocap tailored for reaching. Policies trained with our generated data achieved higher success rates. The mocap data set included motions unsuitable for the walking-reaching task, such as kneeling without transitions from standing, creating a distribution bias. In contrast, our generated data aligning better with the task's requirements, and this indicates our active approach is more efficient and controllable for downstream task. Thanks for watching.